There's a moment, just before the lightning strikes, when the air itself holds its breath. You can feel it, the hairs on your arms standing up, the metallic taste on your tongue, the sky turning that strange greenish gray. That means something powerful is about to happen. That moment, somewhere deep in your bones, you know that whatever comes next will change everything in its path. But here's what nobody tells you about lightning. Here's the secret that generations got backwards, the truth hidden inside one of the most repeated lies in human history. Lightning doesn't forget. On a night just like this one, somewhere in Manhattan, a bolt of electricity tears through the sky. For a fraction of a second, the thunder follows, rattling windows for miles, and then and slams into the spire of the Empire State Building. The flash is so bright, it turns night into day. The echo even fades. Another bolt strikes, same building, same spire, same exact point, where metal meets sky, and again, and pulled the trigger. Yet, we tell ourselves the story, we pass it down like wisdom. Lightning never strikes the same. 20 times this year alone, 20 times that physics has aimed its finger at the same target. We build our understanding of chance and fate and randomness around this simple place twice. We say it at dinner tables and in classrooms. We use it as comfort when bad things. Memorable phrase. But what if I told you it's completely backwards? What if the truth is so much stranger, so much more terrifying and beautiful than the myth we've been telling? Long before we understood electricity, before we even had a word for the electrons dancing through the air, humans looked up at thunderstorms and saw the gods at war. Zeus hurling his bolts in rage. The Norse watched Thor swing his hammer across the sky. Indra rode his elephant through the clouds, his Vajra splitting the heavens. Every culture, every civilization tried to make sense of this violence from above. They were looking for patterns, for meaning, for some way to predict when the sky would open up and reach down with fingers of fire. Fields turned to char and assumed the lightning had moved on. And in their search for patterns, they found one that felt true. They noticed that when lightning struck a tree and split it down the middle, it rarely struck that same tree again. They saw empty and tried to find order in it. So the saying was born, a piece of folk wisdom that spread across continents and centuries. Lightning never strikes the same place twice. It sounded wise. It sounded true. It gave people comfort in an age when comfort was hard to find. But here's what those ancient observers couldn't see. They couldn't see the lightning drawn to the tallest point, like iron to a magnet. They couldn't measure the electrical field building between, again, year after year, with the reliability of clockwork. They couldn't meet Roy Sullivan, cloud and ground. They couldn't watch from space as the same spots on Earth lit up again. Roy was a park ranger in Virginia, a big man with weathered hands and a careful way of times. 7 times the sky reached down and touched him with 30,000 degrees of heat. Watching the sky, and Roy had a problem. Between 1942 and 1977, lightning found him 7 times he should have died. His eyebrows burned off. His hair caught fire so many times he started carrying water with him. 7 times he walked away. His shoes exploded. His shoulders seared like meat on a grill, and each time, after the pain, between pity and fear, faded, and the burns healed, and he went back to work, people would look at him with something, because Roy Sullivan proved something that nobody wanted to believe. Physics finds a target, it comes back. Universe doesn't deal in fairness or chance the way we thought it did. Bars flash that has terrified and fascinated humanity since the dawn of time, from ancient myths to... Hey guys, tonight we begin with one of nature's most misunderstood phenomena, the brilliant modern science. From statistical improbabilities to real-world strike patterns, lightning is one of power, beauty, and surprising truth. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know in the comments where you're tuning in from and what time it is for you. Fascinating to see who's joining us from around the world. Now dim the lights, maybe turn on a together dot, because tonight we're going to unravel one of the oldest myths humans ever told themselves. Fan for that soft background hum, get into your blanket, and let's ease into tonight's journey. We're going to follow the lightning from cloud to ground and discover why it returns to the same that wear its scars like badges, places over and over. We're going to meet the people who survived its touch and the buildings. But first, we need to understand what lightning actually is. We need to see it, not as the angry weapon of gods, but as what it truly represents. Pure physics, pure mathematics, pure inevitable consequence. The storm is building, the pressure is rising, and somewhere above us right now, in the darkness between the clouds and the ground, the air is preparing to tear itself apart. The question isn't whether lightning will strike. The question is where it struck last time, because that's exactly where it's going again. Inside a thundercloud, 5 miles above the earth, a war is happening. Water droplets, the size of pinheads, are being thrown upward by winds moving at 100 miles per hour. They rise into air so cold that they freeze instantly, becoming tiny pellets of ice. Crystals collide with each other thousands of times per second. With each collision, electrons are stripped away. Negative charges gather at the bottom of the cloud like an army massing for. The cloud becomes a battery, a massive, churning battery, storing more energy than a small attack. Positive charges float to the top like cream rising in milk, a nuclear bomb, and below it, the ground begins to respond. The negative charge at the bottom of the cloud pushes electrons in the earth downward, leaving breakdown under the pressure. The surface positively charged, the attraction builds. The electrical field between cloud, ground grows stronger with every passing second. The air itself, normally an insulator, begins to, something has to give. This is where the magic happens, where physics becomes visible fire. A finger of ionized air starts reaching down from the cloud. We call it a stepped leader, and it moves in jumps of about 50 meters at a time, too fast for your eyes to see, too dim to notice against the dark sky. It branches and forks as it descends, testing the air, searching for the path of least resistance. It's looking for a way home. At the same time, from the tallest objects on the ground, streamers of positive charge begin reaching upward, from the spire of the Empire State Building, from the antenna of the CN Tower, from the tip of a lone tree on a hill, from the top of a park ranger's head as he tries to outrun the storm. These streamers stretch up through 30 or 40 meters of air, invisible fingers reaching for the descending leader, and then they touch. The connection happens about 50 meters above the ground, In that instant, a channel of ionized air opens up between cloud and earth, and through that channel, like water through a broken dam, comes the return stroke. This is the lightning you see. This is the bolt that photographs capture and that burns itself into your vision. Electricity racing upward from ground to cloud at 1/3 the speed of light. Channel narrower than your finger. The air temperature spikes to 30,000 Kelvin. To put that in perspective, the surface of the sun is 6,000 Kelvin. Lightning is 5 times hotter than the surface of the sun, 5 times hotter than the thing that lights our entire solar system. This temperature, this impossible heat concentrated in such a tiny space, does something extraordinary. It causes the air to explode. The molecules of nitrogen and oxygen expand so fast, they break the sound barrier. The shock wave that results is what we call thunder, the crack. The light takes about 3/millionths of a second to reach your eyes. The sound traveling and rumble of air being violently pushed aside by temperatures that shouldn't exist on Earth. Much slower, takes about 5 seconds per mile. That's how we count the distance. Flash, then decount. Every 5 seconds is roughly a mile away. But here's where it gets really interesting. Here's where the myth starts to crack. That ionized channel doesn't disappear immediately. For a fraction of a second, maybe 50 milliseconds, it remains a pathway of superheated, electrically conductive air stretching from cloud to ground. And during that time, more charge can flow through it. We call these subsequent strokes the same bolt of lightning, the same channel, conducting multiple discharges, sometimes 3 or 4, sometimes a dozen, each one following the exact same path as the first dot, the same place, struck multiple times in less than half a second. This is why lightning sometimes appears to flicker. You're not seeing one bolt, you're seeing the same channel being used over and over, so fast your brain can barely process the individual flashes. Now imagine you're standing in Manhattan on a stormy summer night, the Empire State, reaching even higher. It's the tallest thing for miles. The electrical field around its tip. Building rises 443 meters into the sky, its spire topped with an aluminum and steel antenna, enormous. When that step leader comes down, searching for a connection, the streamers from the Empire State Building reach higher than anything else in the city. Connect easiest. They connect most often. 20 to 25 times every single year. The sky reaches down and the building reaches back. Sometimes in the same storm, sometimes within minutes of each other, each strike following the same pattern, each strike proving the same point, conductivity and the path of least resistance. Physics doesn't care about our sayings or our wisdom. Physics cares about height, and here's the beautiful, terrible truth that nobody talks about. When lightning hits the Empire State Building, it doesn't damage it. The building was designed for this. Copper strips run down the entire length of the structure, from the tip of the antenna to massive grounding rods deep in the Manhattan bedrock. When lightning strikes, the current flows through the copper, bypasses the building's interior, and disperses harmlessly into the earth. The building doesn't even notice. But Roy Sullivan noticed. Between April 1942 and June 1977, Roy Sullivan was struck by lightning 7 separate times. Not because he was unlucky, not because the universe had it in for him. There's life outdoors, in Virginia, in a state that averages 40 thunderstorm days per year. Often the tallest object in open areas, he was often wearing metal tools. He was often wet from rain. He was, by the simple mathematics of physics, a target. The first time, in 1942, he was hiding in a fire lookout tower when lightning hit it 7 or 8 times in rapid succession. He ran outside and was struck the moment he left the burning nearby tree, deflected through his open window and knocked him unconscious. His truck rolled to a stop near the edge of a cliff while he was out cold. Building. It burned a half-inch strip down his right leg and blew a hole in his shoe. The second time, in July 1969, he was driving his truck on a mountain road. Lightning hit him. The third time was in his own front yard. The fourth while he was in a ranger station. The fifth while he was trying to outrun a storm. The sixth while he was taking a walk. The seventh while he was fishing. 7 times, spread across 35 years. 7 times the math caught up with him. 7 times, he became the path of least resistance between a charged cloud and the ground. Each strike carried about 30,000 amperes of current, enough electricity to power a small town, enough heat to vaporize metal, enough energy to kill him instantly. But electricity is strange. It doesn't always kill. Sometimes it flows through you and out, taking the path through your skin and your sweat rather than through your heart and brain. You survive with burns and scars and memories you wish you didn't have. Roy Sullivan survived all 7 strikes, but he never stopped watching the sky, stopped feeling that charge in the air before a storm. He never stopped being afraid, because he knew something that most people don't believe. He knew that lightning has no memory, but it doesn't need one. It has physics instead, and physics is far more reliable than memory. Every time conditions were right, every time he became the tallest conductor in an electrical, beautiful mathematics field, the lightning came back, not out of malice, not out of fate, but out of simple, inevitable. The same equations that governed his first strike governed his 7th. Nothing changed, except the date. So if lightning strikes the same person 7 times, if it strikes the Empire State Building 20, why do we still believe, against all evidence, that lightning never strikes the same place twice? Then where did the myth come from? 5 times a year, if it returns to the same targets, over and over, with the regularity of a heartbeat, the answer takes us back centuries, to a time before electricity was understood, to the birth of a lie that felt like truth. Picture a farmer in colonial Virginia, standing in his field on a morning in 1723. The storm passed through last night. He heard the thunder rolling across the hills, like distant cannon fire. He saw the flashes lighting up his window, and now, in the gray dawn, he walks out to survey his land and finds it. The old oak tree at the edge of his property, the one that stood there longer than his grandfather could remember, has been split straight down the middle. The bark is peeled back like torn paper. The heartwood is charred black. Steam still rises from the wet wood, where superheated sap boiled and exploded outward. He stands there looking at it, this tree that survived 100 storms, brought down in a single moment by a force he can barely comprehend, and he thinks to himself, well, at least it won't happen again. Lightning never strikes the same place twice. Where did that thought come from? How did it feel so certain, so true, that he never questioned it? The answer lies in something psychologists call the availability heuristic. Dramatic. We remember the singular. We remember the oak tree split in half because it's shocking and visual and changes the landscape we see every day. But we don't remember the church steeple that gets hit every summer. We don't count strikes on the metal windmill. We don't notice when lightning hits the same ridge, the same hill, the same tall pine tree, year after year. Those events blend together. They become background noise. And there's another bias at work, something deeper. Humans are pattern-seeking creatures, survived as a species by finding patterns in nature, by predicting where the food would be, where the danger lurked. But sometimes our pattern-seeking brain finds patterns that aren't really there. The landscape, our brain says, this must be unpredictable, this must be chance. And if it's chance, when we see lightning strike in what appears to be random locations, scattered across a vast, truly random chance, then the odds of it hitting the exact same spot twice must be incredibly small. That logic feels right. It feels true, but it's based on a false premise. Lightning isn't random. In colonial America, this belief became folk wisdom. It was passed down from father to son, from neighbor to neighbor. It appeared in almanacs and farmers' guides. It became the kind of thing everyone just knew, the way everyone knew that moss grows on the north side of trees, or that red sky at morning means sailors take warning. And these sayings survived because they were memorable. They rhymed or had a certain rhythm to them. They were easy to repeat and hard to forget. The truth behind them mattered less than their usefulness as cultural touchstones. Franklin was many things: printer, inventor, diplomat, philosopher. But in the 1750s, but then came Benjamin Franklin, and everything started to change. Obsessed with electricity, this strange force that could be generated by rubbing glass rods, silk, this mysterious power that made sparks jump and gave people shocks, and somehow suspected was the same thing that caused lightning. Most people thought he was crazy. Lightning was the domain of God, not science. It was divine, judgment or natural chaos, not something you could study or understand or control. Franklin didn't care what people thought. In 1752, he conducted an experiment that would change human history. The details have been mythologized and probably exaggerated. Famous story of him flying a kite in a thunderstorm probably didn't happen quite the way we tell. If he'd done exactly what the legend describes, the lightning would have killed him instantly. But he did prove something crucial. He proved that lighting was electrical in nature. He showed that the same sparks you could generate in a laboratory were the same force that split trees, set buildings on fire. He demonstrated that this terrifying power from the heavens followed natural laws. And then he invented something that made the wealthy and powerful of Europe very uncomfortable. He invented the lightning rod. The concept was simple. Put a pointed metal rod at the highest point of a building, connect it with a wire to a metal stake driven deep into the ground. When lightning strikes, the current flows through the rod and wire and dissipates harmlessly into the earth. It worked. It worked so well that buildings equipped with Franklin's rods survived storms, destroyed their neighbors. Ships with lightning rods on their masts made it through electrical to storms that sent other vessels to the bottom of the ocean. But here's what made people uncomfortable. The lightning rod proved that lightning was attracted to specific things: height, metal, pointed objects. It proved that you could predict, with reasonable accuracy, where lightning would strike. If you could predict it, if you could channel it, if you could control it, then it wasn't random at all. The Catholic Church in France initially opposed lightning rods, presumptuous to interfere with divine will. If God wanted to strike your building with lightning, who were you to redirect it? Some priests claimed that church bells could disperse storms, that ringing them during electrical storms was more pious than installing some Americans' metal. The contraption, many bell ringers, died, proving that theory wrong. Survived. Buildings without them burned. The mathematics of it, the sheer practical results. Slowly, grudgingly, the evidence became too strong to ignore. Buildings with lightning rods couldn't be argued away. But the old saying persisted, even as people installed lightning rods on their homes, churches and barns, even as they acknowledged that lightning was attracted to tall metal objects. They still repeated the phrase, "Lightning never strikes the same place twice." Language has a strange inertia. Sayings survive long after the beliefs that created them died. We still say the sun rises and sets, even though we know the earth is rotating. Knock on wood and throw salt over our shoulders, even though we don't believe in the spirits. The lightning myth survived because it served a psychological purpose. It gave comfort. If you were supposedly appeasing, were struck by tragedy, by literal or metaphorical lightning, you could tell yourself that at least it wouldn't happen again. You'd had your share of bad luck. The universe owed you some peace. That's a comforting thought. It's also completely wrong. But there's something else happening here, something more subtle. The myth contains a kernel of truth that makes it stick in our minds. If you're standing in a truly random open field, flat and featureless, the odds of lightning striking the exact same square meter twice are astronomically small, not because lightning avoids that spot, but because there are so many other equally likely spots for it to hit. It's like asking, what are the odds of lightning striking exactly 40.7489 degrees north, 73.9680 degrees west, twice in 1 year? Those odds are tiny, but that's not because lightning avoids coordinates it's already hit. It's because there are infinite coordinates to choose from, are equally likely to be struck. It ignores height, conductivity, isolation, geography. It treats. The myth takes that kernel of truth and extrapolates it incorrectly. It assumes that all locations, lightning, as if it's throwing darts at a map, while blindfolded. But lightning isn't blindfolded. Lightning has perfect aim. It's just aiming at something we couldn't see until we understood physics. By the late 1800s, scientists had figured out the basic mechanics of thunderstorms, electrical discharge. They understood that lightning was following predictable rules, measure the charge in clouds, and calculate the strength of electrical fields. But the myth lived on in rural communities, in folk wisdom, in the sayings parents taught their want to believe in randomness and fairness, and the idea that tragedy won't repeat itself. Even today, with all our satellites and sensors and real-time lightning detection networks, your children, it lived on because changing a culture's beliefs is slow work. It lives on because we still hear people say it. You'll hear it used as a metaphor for rare events. You'll hear it offered comfort after something terrible happens. And every time someone says it, somewhere in the world, lightning is striking the same radio it's been hitting for the past 30 years. Tower it hit last week, the same cell phone antenna it hit yesterday, the same unfortunate tree. The myth is wrong. It's always been wrong, but it's a beautiful kind of wrong. The kind that tells to us something true about ourselves, even as it lies about the universe. We want to believe we're special. We want to believe that suffering is distributed fairly. To believe that if we've been hurt once, we're somehow protected from being hurt again. Lightning doesn't care what we want to believe. Lightning follows the math, and the math says that if you were the tallest conductor in an electrical field yesterday, you'll probably be the tallest conductor in an electrical field tomorrow. Into dust, the same place, over and over, until the building falls, or the tree dies, or the mountain erodes. This is what Franklin understood, and what generations of farmers couldn't see. This is what Roy Sullivan learned the hard way, and what the Empire State Building proves every single year. Nature doesn't deal in fairness. Nature deals in physics, and physics has no memory, but it also has no mercy. It simply calculates the path of least resistance and follows it with absolute, terrifying consistency. If you could see electrical fields the way lightning sees them, the world would look completely different. That flat field you're standing in wouldn't look flat at all. Peaks and valleys of areas where charge concentrates and areas where it disperses. Fence post would glow brighter than the grass around it. A lone tree would shine like a beacon. And the tallest objects, the skyscrapers and towers and mountains, they would burn like stars. A person standing upright would be a pillar of light. They would pull at the charge in the clouds above them, creating streamers and fields so intense that the air itself begins to break down. This is the world lightning navigates, not a world of random chance, but a world of electrical geography, where every object has a value, a probability, a likelihood of being chosen. Height is the first factor, the most obvious, the most important. Lightning is lazy. It wants to travel the shortest distance possible between cloud and ground. There's something tall sticking up, something that closes that gap, even by a few dozen meters. Lightning will find it. The step leader reaching down from the cloud doesn't have to travel far. The streamers reaching up from the ground can extend higher. This is why the Willis Tower in Chicago holds the record for most lightning strikes of any building in America between 2015 and 2020. It was struck about 250 times. That's roughly 50 strikes every single year, one strike every week during storm season. The tower stands 442 meters tall. In a city filled with tall buildings, it's still among the highest points. When storms roll in from Lake Michigan, when the charge builds and the electrical field strengthens, the Willis Tower reaches up into that field farther than almost anything else. It can't help but be struck. It's the tallest kid in class when the teacher is looking for volunteers. It's the nail that sticks up when the hammer comes down. The Empire State Building has the same problem. At 443 meters, counting its antenna, it's been the most photographed lightning target in the world. 20 to 25 strikes every year. Some storms hit it multiple times in a single hour. In 1931, during construction, Workers watched lightning strike the partially completed building again and again. They learned to time their work around the weather. They learned that being up there during a storm was a death sentence, not because of randomness, but because of certainty. The building would be hit. Physics guaranteed it. A tall wooden pole is less likely to be struck than a shorter metal tower. Why? Because but height isn't the only factor. Conductivity matters too. Streamers that reach up from the ground are stronger when they're coming from something that conducts electricity well. Metal, especially pointed metal, creates the strongest streamers. This is why ships at sea are vulnerable. A wooden mast might be tall, but add a metal lightning rod to the top, and suddenly the ship is sending out powerful streamers during every storm. Before Franklin's invention, ships with tall masts and metal fittings were floating targets. Water conducts electricity too, not as well as metal, but far better than dry ground. This is why lightning over lakes and oceans is so dangerous. The water creates a conductive surface that allows streamers to form across a wide area. A person swimming or boating becomes, by default, the tallest thing in that conductive field. Every year, people die learning this lesson. They see a storm approaching across a lake, where think they have time to get to shore. They don't understand that they've become a target the moment they entered the water. Then there's isolation. This might be the cruelest factor of all. A tree in a forest is relatively safe. It's surrounded by other trees of similar height. Field is distributed across all of them. Any one tree is only marginally more likely to be struck than its neighbors. But take that same tree and put it alone in the middle of a field, and it becomes a magnet. The only tall thing for hundreds of meters. Every streamer in that area converges on it. Stepped leader finds it first. This is why golfers are so vulnerable during thunderstorms. They're out in the open, on carefully maintained flat land, often the tallest objects for significant distances. Holding a metal golf club doesn't help. Being near a golf cart with a metal frame doesn't help. The statistics are grim. In the United States, an average of 20 people per year are killed. Lightning. Many of them were caught in open areas, isolated, tall relative to their surroundings. Roy Sullivan understood this better than anyone. As a park ranger, he spent his life in open areas, mountain ridges, forest clearings, the tops of fire towers. He was often alone, often the tallest thing around, often wearing or carrying metal tools. He wasn't cursed. He was simply, tragically, consistently the best conductor in whatever electrical field he happened to be standing in. Now let's talk about geography, because some places on Earth are lightning magnets on a scale that's hard to comprehend. Lake Maracaibo in Venezuela experiences lightning storms 140 to 160 nights per year. That number climbs to 260 nights. That's more than half the year. Every single night, like clockwork, the sky opens up. The phenomenon has a name: Catatumbo lightning. It happens where the Catatumbo River empties into the lake, and it's been occurring for as long as humans have been in the region. For centuries, sailors used it as a navigation beacon. The lightning was so consistent, so predictable, that it functioned as a natural lighthouse visible from over 250 miles away. At its peak, the lightning flashes 28 times per minute, for hours, night after night. Why there? Why that specific location with such obsessive regularity? The answer is topography. Lake Maracaibo sits in a natural bowl surrounded by mountains. Andes to the south, the Perijá Mountains to the west. During the day, the tropical sun heats the lake water to over 30 degrees Celsius. Massive amounts of water evaporate. As evening comes, cool winds blow down from the mountains. They collide with the warm, moist air rising from the lake. The temperature difference is enormous. The moisture content is ideal, and the mountains funnel everything into the same, relatively small area. It's the perfect recipe for thunderstorms. Not just any thunderstorms, but the same thunderstorm in the same place at the same time every single day. The lightning returns with the reliability of the tides. Change any one of those factors and the phenomenon disappears. Keep them constant, and the lightning isn't random. It's the inevitable result of geography plus thermodynamics plus time. In 2010, the lightning stopped for several weeks. People panicked. Scientists worried that climate change had disrupted the pattern permanently. The tourism industry, which had built itself around the phenomenon, faced collapse. Then the rains returned. The evaporation resumed. The temperature difference re-established itself, and the lightning came back exactly as it had for thousands of years, because nothing fundamental had changed. Central Africa, particularly the Congo Basin, is similar. The region sees more lightning than the Democratic Republic of Congo experiences, over 150 lightning flashes per square kilometer anywhere else on Earth. When you average it across the entire continent, the village of Kifuka per year. Why? Same answer. Geography. The Congo River system creates massive evaporation. Equatorial sun provides intense heating. Mountains and highlands create the conditions for powerful updrafts. The result is near constant electrical activity. In North America, Florida holds the title of lightning capital, specifically the area around Orlando and Tampa. The reason is the shape of the peninsula. Sea breezes blow in from both coasts, the Atlantic and the Gulf of Mexico. They meet in the middle, creating a convergence zone where warm, moist air is forced upward. During summer, thunderstorms form over central Florida almost every afternoon. You could set your watch by them. Around 2 or 3 p.m., the clouds begin to build. By 4 or 5 p.m., the lightning starts. By evening, the storms have passed through, leaving behind humid air and the smell of ozone. Afternoon in July. You don't leave your car windows open. You install surge protectors on. People who live there learn to plan around it. You don't schedule outdoor activities for late. Everything valuable, because the power will flicker and spike when the storms roll through. This is life in a lightning hotspot. It's not dramatic or unusual. It's just physics, as regular, predictable as the sunrise. And here's what all these places have in common. From Lake Maracaibo to the Willis Tower, the lone tree in the field. They're not being struck randomly. They're being struck because the conditions that make them attractive to lightning don't change. The mountain doesn't shrink. The tower doesn't get shorter. The lake doesn't move. Electrical properties of metal and water and isolated height remain constant. So the lightning returns again and again, following the same equations it followed yesterday and will follow tomorrow and will follow 1,000 years from now, if these structures still stand. We've built an entire civilization on top of a planet that's constantly being struck by electrical discharge, 8 million lightning strikes per day. Globally, 100 bolts every second, 40,000 thunderstorms active at any given moment. And we've convinced ourselves it's random, that it's unpredictable, that lightning never strikes the same place twice. But lightning knows better. Lightning knows exactly where it's going. It's been hitting the same peaks and towers and trees for as long as they've been tall enough to matter. The landscape hasn't changed. The physics hasn't changed. The math hasn't changed. Terror and beauty. Terror because we realize how vulnerable certain places and people are. Only our understanding has changed, and that understanding comes with a strange mixture. Beauty, because we finally see the invisible rules that govern something we once thought was chaos. The world makes sense. Even lightning makes sense. It's just following a map we couldn't see, until we learn to measure electrical fields and understand the science of storm formation. And once you see that map, once you understand that geography is destiny when it comes to lightning, you can never look at the landscape the same way again. To understand why lightning returns to the same places, you first have to understand what's happening inside the storm itself, and what's happening up there, 5 miles above your head, so violent and powerful that it makes a nuclear explosion look gentle by comparison. It starts innocently enough. A sunny morning, the ground heating up under the summer sun, dark soil and asphalt absorbing energy, warming the air directly above them. That warm air, now less dense than the air around it, begins to rise. At first, it's gentle, a thermal, the kind that birds and glider pilots use to gain altitude without effort. But if conditions are right, if there's enough moisture in that air, something else happens. As the air rises, it cools, and as it cools, the water vapor it's carrying begins to condense, releases heat. That released heat warms the air further, making it rise faster, which causes more condensation, which releases more heat. It's a feedback process, a runaway reaction. What started as a gentle thermal becomes an updraft moving at 60, 80, 100 miles per hour, a river of air flowing upward like an inverted waterfall. The water droplets get carried up with this updraft, small drops at first, barely visible, but as they rise higher and the air gets colder, they start to freeze, not all at once, not uniformly. Transition happens in a zone between 0 and -40 degrees Celsius, a region of the atmosphere where water can exist as liquid, ice, or something in between. This in-between state is where the electricity is born. Some of the water droplets freeze into tiny ice crystals, others remain liquid, supercooled, but not yet solid, and some form a strange hybrid called graupel. These are soft pellets of ice, like tiny snowballs, formed when supercooled water droplets collide with ice crystals and freeze onto them, thrown around inside a cloud by winds that would tear apart a building. They collide constantly. Now you have millions upon millions of these particles, all sizes and shapes and states, being violently, billions of collisions every second. And with each collision, something subtle happens. Electrons are transferred. The lighter ice crystals, being pushed higher by the updraft, tend to gain a positive charge. The heavier grapple pellets, which fall back down through the updraft, tend to gain a negative charge. The exact mechanism is still debated by scientists. Some think it has to do with the warmer parts of the ice transferring negative charge to the colder parts. Others point to the role of supercooled water acting as a medium for electron transfer. The details are complex and not fully understood, but the result is clear. The top of the cloud becomes positively charged. Negatively charged, the cloud transforms into a battery standing 5 miles tall and containing more energy than a small city uses in a day. Directly beneath this battery, the ground responds. It has no choice. Physics demands it. The negative charge at the base of the cloud pushes electrons in the earth downward, away from the surface. This leaves the surface itself with a net positive charge. If you were standing there with sensitive equipment, you could measure the electrical field strengthening. You could watch the voltage gradient climb higher and higher. The air between the cloud and ground, normally an excellent insulator, begins to break down. About 3 million volts per meter. Something critical happens. The electrons in the air molecules get ripped away. The air becomes ionized. It becomes conductive. And then the step leader begins its descent. This is one of the most bizarre things in nature. Series of jumps, each one about 50 meters long, each one happening in about a microsecond. Moves in, starts and stops, too fast for your eyes to register, carving a jagged path through the air, and it branches. The stepped leader splits and forks and divides as it searches for the path. Of these branches will go nowhere. They'll fizzle out. Only one will make the connection. But here's the crucial part. The stepped leader is moving toward the strongest electrical field, least resistance, like a tree growing downward, like roots searching for water in reverse. Gradient. It's being pulled toward the largest accumulation of positive charge. And where do you find the largest accumulation of positive charge on the ground? At the tips of tall, pointed, conductive objects, at the top of the Empire State Building, summit of a lone tree, at the highest point of whatever structure happens to be in the area, reaching up to meet it. These are ribbons of ionized air, glowing faintly, extending upward from. As the stepped leader gets close, within about 30 to 50 meters of the ground, streamers begin. Anything tall enough to generate them. The taller and more conductive the object, the stronger and longer these streamers. The Willis Tower sends up streamers that reach 50 meters into the air. A person in an open field might generate streamers a few meters long. A car, being low to the ground and surrounded by other objects, generates much weaker streamers. When one of those streamers connects with the step leader, everything changes. Suddenly, there's a complete circuit from cloud to ground, a channel of ionized air, conductive, ready to carry current, and through that channel comes the return stroke. This is the lightning you see. This is the bolt that lights up the sky. Current racing from ground to cloud, driven by the potential difference between them, traveling at about 100 million meters per second, 1/3 the speed of light. In that narrow channel, maybe an inch wide, the temperature spikes to 30,000 Kelvin in less than a millisecond. The air doesn't just heat up, it explodes. The molecules of nitrogen and oxygen are torn apart and then slammed back together, expanding with such force that they create a shock wave traveling faster than sound. That shock wave is thunder. The crack you hear isn't the lightning itself, it's the air being violently displaced by temperatures that have no business existing in Earth's atmosphere. But the return stroke isn't the end. That ionized channel, that pathway from ground to cloud, remains conductive for a brief moment, and if there's still charge available in the cloud, these are called subsequent strokes. They follow the exact same path as the first return stroke. Current can flow, using the same channel, striking the same point on the ground. Sometimes there are 3 or 4, sometimes a dozen or more, each one separated by about 50 milliseconds, adding more energy, more heat, more violence to the same pathway. This is why lightning sometimes appears to flicker or pulse. You're seeing multiple strokes using the same channel so rapidly that your brain can barely distinguish them. And then, in less than half a second, it's over. The channel cools. The air returns to its normal, insulating state. The thunder rolls away into the distance. The storm moves on. But the conditions that created that lightning haven't changed. The updraft is still running. Another step leader will begin its descent. Ice is still colliding. The charge is still separating. 5 minutes from now, or 5 seconds, and if the tallest object in the area is still the tallest object, if the most conductive surface is still the most conductive, if the electrical geography hasn't changed, then the next bolt will find the same target, not because it remembers the first strike, not because it's following some cosmic rule about fairness or distribution, but because the physics that guided the first bolt will guide the second bolt in exactly the same way. The Willis Tower doesn't become shorter between strikes. The Empire State Building doesn't suddenly lose its conductivity. The lone tree in the field doesn't shrink down to hide among the grass. They remain what they are: tall, conductive, isolated, the best possible targets in their respective electrical fields. And so the lightning returns in the same storm, hours apart or seconds apart, following the same mathematics with absolute reliability. This is what makes the myth so frustrating to anyone who understands storm physics. That lightning sometimes strikes the same place twice. It's that lightning preferentially strikes the same places over and over, because those places are, by definition, the most likely targets. A single thunderstorm can produce hundreds of lightning strikes. If one of those strikes hits the tallest object in the area, what are the odds the next strike will also hit the tallest object? Small, not unlikely, nearly certain. The storm doesn't care about our sayings. The charge separation doesn't consult folk wisdom. The step leader doesn't check whether it's allowed to return to a previous target. It simply follows the electrical field gradient down to the point of highest potential. Point is the same as last time. So be it. This is the anatomy of a storm. This is the mechanism that powers the most spectacular light show on Earth. And once you understand it, once you see how the process works from start to finish, the old myth becomes not just wrong, but almost laughably backwards. Lightning doesn't avoid striking twice. It specializes in it. It's drawn to the same targets by the same forces that drew it there the first time. The storm is a machine, churning out bolt after bolt, each one following the same physical laws, each one finding the same optimal paths. And somewhere in that storm, in the updrafts and downdrafts and swirling chaos of ice, water, new charge is already separating. New electrical fields are already building. New stepped leaders are already preparing to descend. The next strike is coming. The only question is whether anything has changed since the last one, and if nothing has changed, if the landscape is the same, and the conductors are the same, and the heights are the same, then the answer is already written in the electrical fields. Same place, same physics, same inevitable result. A single lightning bolt is impressive, but a storm that produces hundreds of them, hour after the hour, targeting the same locations with mechanical precision, that's something else entirely. Supercell thunderstorms are nature's most efficient killing machines. They can last for 6, 8, 10 hours. They can travel hundreds of miles, and during their lifetime, they can produce more lightning strikes than some cities see in an entire year. The key to their longevity is rotation. While ordinary thunderstorms rise straight up and collapse within an hour, supercells have a rotating updraft called a mesocyclone. This rotation, caused by wind shear at different altitudes, organizes the entire storm system. It separates the updraft from the downdraft, preventing the storm from choking on its own rain. The result is a self-sustaining electrical factory that can operate all afternoon and into the night. Inside a supercell, the charge separation becomes more efficient. The rotating updraft keeps the ice particles suspended longer, giving them more time to collide and transfer electrons. Positive and negative regions become more distinct, more powerful, creating stronger electrical fields. This is the flat, spreading top of the thunderstorm that can extend for 50 or 100 miles downwind. Count out. And at the top of the storm, something beautiful and deadly happens. The anvil cloud spreads. It forms when the updraft hits the tropopause, the boundary between the troposphere, stratosphere, and can't rise any higher, so it spreads horizontally instead, like water hitting a ceiling. Inside this anvil, lightning travels horizontally for miles. These cloud-to-cloud strikes are actually the most common type of lightning, far more frequent than the cloud-to-ground bolts we focus on wood, but we don't notice them as much because they're hidden inside the clouds, illuminating them from within like lanterns. Most people don't realize those strikes aren't randomly distributed across the landscape below. A single supercell can produce 50, 100, 200 cloud-to-ground strikes in an hour. And here's what: they're concentrated in specific areas determined by the storm's position and the geography beneath it. If the storm is sitting over Willis Tower for 20 minutes, the tower might be struck a dozen times. If it moves slightly east, the strikes shift to a different cluster of tall buildings. The storm doesn't remember where it struck before. It simply recalculates based on current conditions and strikes whatever presents the best target at that moment. But there's another type of storm system that's even more relevant to our story: the multi-cell cluster. These are groups of thunderstorms at different stages of development, all traveling together. One cell matures and begins to decay. A new cell forms next to it, then another, then another. The result is a conveyor belt of electrical activity that can pass over the same area for hours. Imagine you're the Empire State Building. A thunderstorm approaches from the west. It strikes you 3 times as it passes overhead. Then it moves east and begins to weaken, but behind it, then another cell, then another. A new cell is already forming. 20 minutes later, it arrives. It strikes you 4 more times. By the end of the evening, you've been struck 15 times, not because you were unlucky, because the storm had it in for you. But because you remain the tallest, most conductive object in your area, while multiple storms pass through, each one independently calculating the same optimal target. This is what happened to the CN Tower on August 24th, 2011. A multi-cell storm system moved on across Toronto and sat over the tower for 84 minutes. During that time, the tower was struck 52 times, 52 separate lightning events, each one finding the same 553-meter tall metal antenna sticking up into the electrical field. One strike every 97 seconds for an hour and a half, like a metronome, like a heartbeat. Physics doing what physics does. The storm wasn't targeting the tower. The storm was simply producing lightning based on charge separation in the clouds, and that lightning was finding the path of least resistance, which happened to be the same path it found 30 seconds ago and would find again 30 seconds later. Now think about probability for a moment. If lightning were truly random, if it really did avoid striking the same place twice, what would be the odds of the CN Tower being struck 52 times, 84 minutes, every week for a year? The calculation would be absurd, astronomically small. You'd be more likely to win the lottery. But if lightning follows physics, if it seeks the tallest conductor in its area, then the odds of the CN Tower being struck 52 times during a storm that produces hundreds of lightning bolts becomes not just likely, but inevitable. This is the difference between randomness and determinism. Random events have no memory and no pattern. Deterministic events follow rules, and those rules produce patterns that look deliberate, even though they're just following mathematics. A thunderstorm over Chicago will strike the Willis Tower multiple times, not because the tower is accursed, but because the tower is 442 meters tall and nothing else around it even comes close. The electrical field gradient points straight at it like an arrow on a map. During a typical summer in the Midwest, storm systems can produce thousands of lightning strikes as they move across hundreds of miles. Most of these strikes hit nothing noteworthy. Empty fields, forest canopy, lakes. They leave no trace, and no one remembers them. But a few dozen of those strikes will hit something tall: a radio tower, a wind turbine, a grain elevator. And because those structures remain in place, because they don't move or shrink, disappear, the next storm will find them again. Over the course of a summer, a single radio tower might be struck 30 or 40 times, not spread evenly across the landscape, not distributed fairly among all the possible targets, concentrated on that one tower, because that's where the physics leads. And here's something that really drives the point home. You can predict it. Modern lightning detection networks can tell you with reasonable accuracy which structures in a given area are most likely to be struck. They look at height, conductivity, isolation, calculate the electrical field strengths. They run the numbers, and their predictions match reality. The towers they flag as high risk are the ones that get struck repeatedly. The buildings they mark as moderate risk see occasional strikes. The low-lying areas see almost none. If lightning were random, these predictions would be useless. You couldn't forecast where it would strike any better than you could forecast lottery numbers. But lightning isn't random. Lightning is physics, and physics can be predicted. This creates an interesting situation for people who work on tall structures. Possibility for them, it's a certainty. The workers who maintain broadcast towers know they'll be dealing with lightning damage. Question isn't if, but when and how severe. They plan for it. They budget for it. They install protection systems and redundant equipment because they know mathematically that lightning will return to their tower again and again. The same is true for wind farms. Modern wind turbines can be 100 meters tall or more. Blades sweep through a huge volume of air, and they're often placed on ridges and hilltops, the highest points in their regions, specifically to catch more wind. This makes them perfect lightning targets. A wind farm with 50 turbines might see 200 or 300 systems built into the blades and towers. The manufacturers know that if you build something, lightning strikes in a bad year. The turbines are designed for this. They have lightning protection. Pull and put it on a hilltop. Lightning will find it. Insurance companies understand this too. They charge higher premiums for structures that are tall, isolated, and in areas with high thunderstorm frequency. They've crunched the numbers. They know that a cell tower in Florida is far more likely to be struck than a cell tower in California. They price their policies accordingly. This isn't guesswork. This isn't superstition. This is actuarial science based on decades of data showing that lightning returns to the same types of structures in the same types of locations year after year. The myth says lightning never strikes the same place twice. The insurance industry, which literally bets money on these things, knows that's backwards. Lightning strikes the same places constantly, predictably, reliably enough to build business models around. So when we talk about a lightning storm, we're not talking about chaos. Highly organized system that produces electrical discharges according to specific rules, and those discharges find targets according to those same rules, and if the targets remain constant, all the strikes will concentrate on them with mathematical precision. The storm doesn't care about fairness. It doesn't distribute its strikes evenly. It doesn't avoid places it's already hit. It simply follows the electrical field gradients down to the points of highest charge concentration, which are almost always the same points they were an hour ago, yesterday, or last year. And when the storm finally moves on, when the updrafts weaken and the charge separation stops and the thunder fades into the distance, the targets remain. The towers, the buildings, the trees, the mountains, still tall, still conductive, still isolated, still waiting for the next storm to arrive and do exactly what the last storm did. Because that's what storms do. That's what lightning does. It finds the same paths over, not through memory or malice, but through the simple, elegant, brutal efficiency of physics, seeking the path of least resistance. And the path of least resistance doesn't change just because you've used it before. Roy Cleveland Sullivan didn't want to be famous. He didn't want to be in the Guinness Book of any of the other nicknames people gave him, world records. He didn't want to be known as the human lightning rod or the spark ranger. He just wanted to do his job and go home to his family without being electrocuted. But the universe, or more accurately, the physics of electrical discharge, had other plans. April 1942, Roy was 30 years old, working as a ranger in Shenandoah National Park in Virginia. A thunderstorm rolled through the mountains, and he took shelter in a newly built fire lookout. The storm hit the tower 7 or 8 times in rapid succession. Fire jumped across the metal tower. The tower had no lightning rod yet, that was scheduled to be installed next month. He made it about 10 feet before lightning struck him directly. Framework. The air inside filled with the smell of ozone and burning wood. Roy realized he was in more danger inside than outside, so he ran for the door. The bolt hit his right leg, burned a half-inch strip down to his foot, and blew a hole through his shoe. His big toenail turned black and fell off a week later. He survived, confused and hurting, but alive, wondering what the odds were of that happening. He would spend the next 35 years learning that the odds weren't what he thought they were. July 1969. Roy was driving his truck along a mountain road. A storm was brewing, but he was inside a vehicle which normally offers good protection. The metal frame acts as a Faraday cage, conducting electricity around the outside rather than through the interior. Head knocked him unconscious and set his hair on fire. The truck, with no one controlling it, but Roy's window was open. Lightning hit a tree next to the road and jumped through the open window. It struck Roy in the rolled forward and came to rest near the edge of a cliff. When Roy woke up, his eyebrows were gone. His hair was singed. His watch had stopped. He was maybe 20 feet from a drop that would have killed him more surely than the lightning did. July 1970. Roy was in his own front yard, his own property, not on a mountain ridge, not in an exposed area, just standing outside his house. Lightning struck a nearby transformer, and the current arced from the transformer to his left shoulder, searing it like meat on a grill. This was the strike that made him start to wonder if something was wrong. April 1972. Roy was inside a ranger station, inside a building, surely safe, right? The storm hit. Years. That seemed like more than chance. That seemed like something was going on. Fire again. He ran to the bathroom to put it out, but his head wouldn't fit under the faucet. The building, and somehow the current found its way to where Roy was sitting. It set his hair on, to use wet towels pressed against his scalp, while the smell of burnt hair filled the small room. After this fourth strike, Roy started carrying a can of water with him, just in case. He also developed a habit of watching the sky obsessively. When storm clouds appeared, he would find somewhere to hide. He started believing that maybe, just maybe, lightning was following him. He wasn't wrong, but he also wasn't being targeted. He was simply consistently in the wrong place. August 1973. Roy saw a storm cloud forming while he was out on patrol. He tried to outrun it. He jumped into his truck and drove away as fast as he could. When he thought he was at a safe distance, he got out. The lightning hit him immediately. It traveled down his left arm and left leg, blowing his shoe off. His hair caught fire again. He grabbed his emergency water can and doused himself, standing there in the rain, wondering what he'd done to deserve this. The thing is, he hadn't done anything. He was just tall, often alone, frequently in elevated areas, regularly caught in storms, because his job required being outdoors in the mountains of Virginia, a state that sees 35 to 45 thunderstorm days per year. He was a statistical inevitability. June 1976. Roy was taking a walk. He tripped and injured his ankle. As he was getting back to down, the lightning caught him anyway. It hit him and set his hair on fire once more. His feet. He saw storm clouds approaching. He tried to run, but the injured ankle slowed him. Nervous, jumpy, he would see clouds on the horizon and immediately go inside. He refused to attend outdoor events if there was even a chance of rain. His friends and family tried to be. People who knew Roy said he became a different person after the 5th and 6th strikes. Understanding, but it was hard because they didn't really believe it could happen again. 5 times, 6 times, that was enough. Right? Lightning never strikes the same place twice. Surely he'd used up his quota of bad luck. June 25th, 1977. Roy was fishing at a small lake. It was early morning. The sky was clear when he arrived, but storms in the mountains can form quickly, and by mid-morning, the clouds had rolled in. The lightning hit the top of his head. It traveled down through his body, burning his chest, stomach. His hair, which had grown back thin and patchy from all the previous burns, caught fire. For the 7th time, Roy Sullivan had just become the only person in recorded history to be struck by lightning 7 times and survive all 7 strikes. Angry gods, he wasn't the universe's punching bag. But here's what's important to understand. Roy wasn't cursed. He wasn't being punished by. He was a park ranger in a mountainous, storm-prone region. He spent his working life outdoors, often alone, often on ridges and peaks and open areas. He was frequently the tallest conductive object in his immediate vicinity. He worked in a job that required him to be outside during all weather conditions, including the afternoon thunderstorms that regularly form over the Virginia mountains. Every single one of those strikes can be explained by physics, not fate, not cosmic injustice. Just height, plus conductivity, plus isolation, plus exposure time equals target. The math that guided lightning to the Empire State Building was the same math that guided it. Roy Sullivan. The only difference was that buildings don't feel pain and don't develop trauma from repeated strikes. Roy did. In the years after the 7th strike, he became increasingly isolated. People avoided him, not out of cruelty, but out of fear. They genuinely believed that being near him during a storm would. It wasn't, but the belief was strong enough that Roy found himself alone more often than not. Increased their own risk of being struck. They thought his bad luck was contagious. Even his wife, who had herself been struck once while hanging laundry, kept her distance from him when storms approached. The psychological toll was immense. Roy had survived 7 lightning strikes, each one capable of killing him instantly, but he couldn't survive the loneliness and fear and constant vigilance that came with understanding just how vulnerable he was. On September 28, 1983, Roy Sullivan died from a self-inflicted gunshot wound. He was 71 years old. The official cause was listed as depression related to unrequited love, but those who knew him said the lightning had taken its toll long before. His story is tragic, but it's also instructive. When lightning strikes a person, the current takes the path of least resistance through the body. If you're unlucky, the current finds a path through your body, through your heart, stopping it, usually along the surface where sweat and moisture provide conductivity, flashes over your skin and exits through your feet without causing major internal damage, through your nervous system, scrambling the signals that keep you breathing, brain causing damage that might not show up for days or weeks. Survivors of lightning strikes often report long-term effects, memory problems, difficulty concentrating, personality changes, chronic pain. The electricity doesn't just hurt you in the toll moment, It leaves scars you can't see, damage to nerves and brain tissue that never fully heals. Roy experienced all of this, multiplied by 7, each strike added to the accumulated damage. Each one reinforced the trauma, each one proved that the myth was wrong, and that he, specifically he, was vulnerable in a way that defied the comforting story everyone else believed. Lightning doesn't strike the same place twice, they said, but Roy Sullivan was proof that it does. 7 times proof. 7 separate incidents spread across 35 years, each one following the same physics, each one finding him because he remained consistently a valid target. There are other multiple strike survivors, people hit 2 or 3 times over their lives, but 7 is the record. 7 times Roy stood in the wrong place at the wrong time, and 7 times electrical field found him and connected cloud to ground through his body. He didn't deserve it. He wasn't being singled out by fate. He was just consistently and tragically the tallest conductor in various electrical fields over the course of a long career spent outdoors in a storm-prone region. The same factors that make the Empire State Building a target made Roy Sullivan a target: height, conductivity, isolation, exposure. The same physics that brings lightning back to the CN Tower again and again brought it back to Roy. The myth says it shouldn't happen. The math says it will. And Roy Sullivan, more than anyone in history, proved that the math wins every single time. There's something almost defiant about skyscrapers. They reach up into the sky as if challenging the storms to do their worst, and the storms accept that challenge again and again. With mathematical precision. The Willis Tower in Chicago stands 442 meters tall, counting its antennas. It's not the tallest thing in Chicago, and Chicago sits on the shore of Lake Michigan, where moisture-laden building in the world anymore. But for lightning, that doesn't matter. What matters is that it's the air collides with urban heat to create spectacular thunderstorms. Between 2015 and 2020, the Willis Tower was struck approximately 250 times. That's 50 strikes per year on average. About 1 strike per week during storm season. The building has been hit so many times that researchers use it as a natural laboratory for studying lightning behavior. Current, the voltage, the duration, the number of return strokes. Every strike adds data to our. When lightning hits the Willis Tower, sensors throughout the building record the event. Understanding of how lightning works. The building has become one of the most thoroughly documented lightning targets in the world. But the Willis Tower wasn't designed to study lightning. It was designed to survive it. The protection system is elegant in its simplicity. Air terminals, metal rods, and points at the highest parts of the structure provide the best launching points for streamers. These connect to a network of conductors, heavy cables that run down the exterior and interior of the building. Those conductors feed into grounding electrodes buried deep in the earth, beneath the foundation. When lightning strikes, the current flows through this system, rather than through the building itself. The electricity takes the path of least resistance, which is the path humans have carefully constructed for it. The current bypasses the offices, the elevators, the electrical systems, people. It goes straight from sky to ground without causing damage. This is Franklin's lightning rod, scaled up to protect a building that weighs over 200,000 tons. The Empire State Building has a similar system, and it needs one at 443 meters tall, with its houses thousands of people. Antenna, standing in the heart of Manhattan, it's been a lightning magnet since before it was fully finished. During construction, 1931, workers watched lightning strike the partially completed structure. Construction crews watched from safer, lower buildings nearby. The engineers knew what they were building. They knew it would be struck. They planned for it from the beginning. Repeatedly, there are photographs from that era showing bolts hitting the steel framework, while the building's antenna, added in the 1950s for broadcasting, actually serves double duty, ground, and it works. 20 to 25 times per year, the building is struck, sometimes massive lightning rod. The entire spire is designed to attract lightning and channel it safely multiple times in a single storm, sometimes multiple times in a single hour. In 2011, a photographer captured the building being struck 3 times in rapid succession. Images went viral because they're spectacular, bolts of electricity wrapping around the iconic structure, illuminating it against the dark sky. But for the building's engineers, it was just another Tuesday. The people inside don't even notice most strikes. There might be a brief flicker of the lights, faint vibration, but the protection system does its job so well that a lightning strike to the Empire State Building is less disruptive than someone tripping a circuit breaker. One World Trade Center, the tallest building in New York at 541 meters, has joined this club of frequently struck structures. Between 2015 and 2020, it was struck 189 times. That's about 38. The architects knew this would happen. The entire top section of the building is essentially 1 strikes per year. The building opened in 2014, and almost immediately, lightning started finding in fall. Giant lightning rod. The spire, which extends 124 meters above the main roof, is made of steel and designed specifically to handle repeated strikes. It's not decorative, it's functional, saying to every thunderstorm that passes over Manhattan, "Here, strike here, we're ready." In Toronto, the CN Tower holds perhaps the most impressive record. At 553 meters, it's not just a building, it's a communications tower, a tourist attraction, and an antenna farm all in one. It gets struck an average of 75 times per year. Days when the tower is struck multiple times as storm after storm rolls through. 75 times. That's more than once a week during the active season. The tower has been monitored for lightning strikes since it opened in 1976. For over 30 years, researchers have been recording every strike, studying the patterns, understanding the physics. The CN Tower has taught us more about lightning behavior than almost any other structure. Earth. On that record-breaking day in August 2011, when the tower was struck 52 times in 84 minutes, every single strike was documented. High-speed cameras captured the formation of the stepped leader, the connection with the streamers, the return stroke, the subsequent strokes. Scientists watched in real time as lightning demonstrated its absolute consistency in choosing the same target over and over. The tower's protection system is similar to other tall structures, but scaled to handle the incredible frequency of strikes. Copper strips run the entire 541 153-meter height of the tower beneath Toronto. When lightning strikes, and it will strike, the current has a clear, low resistance, the tip of the antenna down to massive grounding rods that extend deep into the bedrock, path to follow. This is the key insight that Franklin gave us 270 years ago. You can't stop lightning from striking. You can't convince it to go elsewhere, but you can give it a path that doesn't destroy what you've built. Modern lighting protection has evolved beyond simple rods and cables. Some systems use early streamer emission technology, which sends up streamers slightly before natural streamers would form, theoretically giving the protection system a head start in capturing the lightning. Other systems use charge dissipation, trying to reduce the electrical field gradient and make the structure slightly less attractive to lightning. But the basic principle remains the same. If you build something tall, especially something tall and made of metal, in an area that experiences thunderstorms, lightning will find it. The question: aircraft face a similar challenge. Commercial jets fly through thunderstorms regularly. They can't. Is whether you're prepared for that inevitability. Once per year on average. Always avoid them, especially during takeoff and landing, and they get struck by lightning. Modern aircraft are designed for this. The aluminum skin conducts electricity well, allowing the current to flow around the outside of the fuselage rather than through the interior. Composites, materials which are becoming more common in new aircraft designs, require embedded conductors to provide the same protection. When lightning strikes an aircraft, the current typically enters at an extremity like the nose. Wingtip flows along the skin and exits at another extremity like the tail, protected by multiple layers of shielding. The avionics are hardened against electromagnetic pulses. The whole system is engineered to handle what is fundamentally an inevitable event. Pilots report that a lightning strike feels like a small bump or a bright flash. Passengers might not notice it at all. The aircraft continues flying normally because engineers knew this would happen and designed accordingly. Wind turbines present an interesting case. These structures are tall, often placed on hills, ridges to catch more wind, and topped with long conductive blades that sweep through huge volumes of air. They're almost perfectly designed to attract lightning. A typical wind farm might see hundreds of strikes per year across all its turbines. Take the most damage because they're moving targets. Lightning might strike a blade at one storm. The blades themselves need to be replaced periodically because of cumulative lightning position during one storm, and strike a different blade in a different position during the next. Damage. The economics of this are fascinating. Wind farm operators know exactly how often their maintenance costs and insurance premiums. Lightning isn't a disaster for them. It's a predictable. Turbines will be struck. They know how much damage to expect. They factor this into operating expense, like changing oil in a car, that certain structures will be struck repeatedly. You stop treating each strike as a surprising. This is what happens when you truly understand that lightning isn't random, when you accept event and start treating the whole phenomenon as something manageable. The myth says lightning never strikes the same place twice, implying that once you've been hit, you're somehow safe. The reality, understood by every architect and engineer who designs tall structures, is exactly the opposite. Once you've been struck, it proves you're a good target. You'll be struck again. So they build protection into the structure from the beginning. They don't hope lightning will choose a different building. They assume their building will be chosen repeatedly. And this is why modern skyscrapers are so safe, despite being struck constantly. This is why aircraft prepare for it, can fly through storms without falling from the sky. This is why communication towers can stand on mountaintops for decades, struck thousands of times, and continue functioning. We've learned to live with lightning by accepting what it is, not a curse, not random misfortune, but a predictable physical phenomenon that follows clear rules and can be defended against through engineering and understanding, safely to ground, and the cycle repeats over and over, proving every single time that the buildings stand tall, the lightning strikes them, the protection systems channel the energy, saying, had it exactly backwards. Lightning doesn't avoid places it's already struck. It returns to them with the reliability of a heartbeat, following the same electromagnetic rules that have governed electrical discharge since before humans built anything tall enough to notice. There's a network of sensors scattered across North America, thousands of them, constantly. Lives are listening for lightning, not with ears, but with electromagnetic detectors that pick up the radio waves produced by every lightning strike within hundreds of miles. Each sensor records the exact time it detected the signal, because radio waves travel at the speed of light, and because we know exactly where each sensor is located, simple mathematics, and it can triangulate the location of the strike. 3 or more sensors detecting the same event, you can pinpoint the lightning's location to within a few meters. This is the National Lightning Detection Network, operated by NOAA and private companies, been running since the 1980s, getting more sophisticated with each passing year. Lightning strike in the continental United States is detected, located, and logged. Millions of strikes per year, decades of data showing exactly where lightning goes and how often, and the data reveals what we've been saying all along. Lightning isn't random. It has favorite. The maps are striking in their clarity. Bright spots appear where tall structures stand. Radio, targets, same locations. The surrounding areas show scattered strikes, but the towers shine like beacons, hit dozens or hundreds of times, while the ground around them might not be struck at. Or towers, cell phone antennas, wind turbines. These structures light up year after year in the latitudes. This data is used by meteorologists, insurance companies, power utilities, and anyone else who accurate. Tell a lightning scientist the height, conductivity, and isolation of a structure. Give them needs to understand lightning risk, and the predictions based on this data are remarkably the average number of thunderstorm days in that area, and they can estimate how many times, not perfectly. Weather has variance, but close enough that the predictions are useful. Close per year that structure will be struck, enough that you can make business decisions based on them. But detection networks only tell us where lightning struck in the past. Can we predict where it will strike in the future? Can we see it coming? The answer is yes, but with limitations. Modern weather radar can track thunderstorms in real time, showing the precipitation, updrafts, the rotation. Meteorologists can watch a storm form and strengthen and move across the landscape. They can see when conditions are right for lightning. Geostationary satellites, parked 22,000 miles above the Earth, carry lightning mappers, detect the optical flash of lightning from space. The GOES are a series of satellites launched in ocean, track them as they move toward land, and monitor them until they dissipate. Recent years can see lightning over entire hemispheres. They watch storms develop over the. When a storm's lightning activity suddenly increases, it often means the storm is intensifying. Updrafts are strengthening, and the charge separation is accelerating. Flash rate tells meteorologists that something significant is happening inside that cloud, this can be an early warning sign of severe weather, even tornadoes. The rapid increase in where the next bolt will hit, but of dangerous conditions, we can tell people that a storm is. This gives us advance warning, not of individual strikes. We can't predict exactly when, from producing frequent lightning, and that they should take shelter. And we have rules for personal safety that save lives every year. The 30-30 rule is simple. When you see lightning, count the seconds until you hear thunder. It's less than 30 seconds. The storm is close enough to be dangerous. Take shelter immediately. And after the last thunder, wait 30 minutes before going back outside. Storm. Thunder travels about 1 mile every 5 seconds. If you're hearing thunder within 30, this rule is based on the speed of sound and the distance lightning can travel from its parent, turning downward. The sky might be clear overhead. The storm might look far away, but the seconds. The lightning is within 6 miles, and lightning can strike up to 10 miles away from the brain shaft, something we call a bolt from the blue dot. These are strikes that come from the anvil of the storm, traveling horizontally for miles before in the region needs to know that dot. The myth matters because myths always matter. They shape culture, influence behavior, transmit values across generations. When the myth is harmless, maybe that's fine. Actively wrong about something dangerous, it needs to be corrected. We've spent 19 sections building the case. Roy Sullivan struck 7 times. The Empire State Building struck 25 times per year. The Willis Tower struck 50 times per year. The CN Tower struck 52 times in 84 minutes. Lake Maracaibo struck 40,000 times per year for thousands of years. The evidence is overwhelming. Lightning doesn't avoid places. It's already struck. It seeks them. Goes out, not consciously, but through the blind mathematics of electrical field gradients, finding paths of least resistance. The myth told us nature was random and capricious. The truth is that nature follows rules, even when those rules produce results that seem unfair. The same tall tower that was struck yesterday will be struck again tomorrow because nothing about it has changed. Remains, the conductivity remains, the isolation remains, therefore the target remains. This isn't bad news. Predictability is good. Predictability means we can prepare, can protect, and can make informed decisions about risk. The myth told us we couldn't predict lightning, couldn't defend against it, couldn't do anything, but hope we weren't chosen. The truth tells us we can predict it remarkably well, can defend against it effectively, can reduce risk through understanding and engineering. That's why the myth matters, not just because it's wrong, but because believing it prevents us from taking actions that save lives, because it encourages complacency instead of caution, because it makes lightning seem more mysterious and less manageable than it actually is. We understand lightning now, not perfectly, There are still details being worked out, but well enough to know where it goes, and why, and how often, well enough to protect the structures that need protecting, well enough to teach people how to stay safe. The myth served its purpose for a long time. It gave people a framework for thinking about something they didn't understand. It provided comfort in an age when comfort was scarce. We've outgrown it. We have better frameworks now, better understanding, better tools. It's time to let the myth die, not with anger or mockery, but with appreciation for what it tried to do and recognition that we've moved beyond it. We know better now. We can do better now. Lightning strikes the same places over and over. That's not a curse. It's a pattern. Can be understood, predicted, and planned for. The myth told us to hope we wouldn't be struck twice. The truth tells us to understand why we were struck once and change the conditions that made us a target. The truth puts control back in human hands, not control over lightning. We'll never have that, but control over our choices, our preparations, our responses. That's why the myth matters, because replacing it with truth changes how we relate to one of nature's most powerful phenomena, changes us from passive victims, hoping for cosmic fairness, to active agents, managing risk through understanding. The myth is dying. Good. Let it die. Replace it with knowledge, with data, with the simple, elegant truth that lightning follows physics, and physics follows rules, and those rules can be learned. Lightning knows where to strike. Now we know too. That knowledge is worth more than any comforting myth ever was. The storm is passing now. You can hear it in the thunder, the way it's growing more distant, rumbles stretching out longer as the sound travels farther to reach you. The lightning still flashes on the horizon, illuminating clouds from within, but the danger has moved on. For now. But you know something different now than you did when this journey began. When the next storm comes, when the clouds build and the electrical fields strengthen and the stepped leaders begin their descent, they'll find the same targets. The Willis Tower will be struck again. The Empire State Building will light up again. Count Roy Sullivan's story ended in tragedy, but his experience taught us something crucial. Not cursed by gods or fate, he was simply, consistently, the best conductor in various electrical fields over the course of a long career. The same physics that guided the first bolt to him guided the seventh. Nothing supernatural, nothing mysterious, just height and conductivity, isolation intersecting with Virginia's thunderstorm season year after year. He's gone now, but the lesson remains. Lightning doesn't strike randomly. It doesn't avoid places it's already hit. It returns to them with the reliability of planetary orbits, following electromagnetic rules that have governed electrical discharge since Earth first had an atmosphere capable of creating storms. The Empire State Building stands tonight as it stood last night and will stand tomorrow night. Still 443 meters tall, still metal, still the most prominent structure in its part of Manhattan. Storms roll in from the west. When the charge separation in those clouds reaches the breaking point, the streamers will reach up from that spire, and the step leaders will find them, and the connection will be made. Take again. The 26th time this year, or the 30th, or the 15th. Certainty doesn't. The building will be struck because the physics demands it, because tall, conductive, isolated objects in electrical fields our targets, not by choice, but by nature. And all across the world, the same story plays out. Lake Maracaibo will see its lightning tonight, as it has for thousands of years. The Catatumbo River will empty into the lake under a sky split by electrical discharge every few seconds. The fishermen will time their work around it. Tourists will photograph it. The locals will barely notice because it's just weather, as predictable as sunrise. The Congo Basin will light up with strikes, concentrated in patterns that match the topography. The Florida Peninsula will see its afternoon storms, building like clockwork during summer months. Radio towers across the Great Plains will be struck and will continue functioning because they were designed for this, because engineers understood what was coming. This is the world we actually live in, not the world of the myth, where lightning is mysterious, capricious, and never returns, but the real world, where lightning follows rules and returns constantly and can be predicted with reasonable accuracy. We wanted to believe in randomness because randomness feels fair. If lightning is random, then being struck is just bad luck, not your fault, not something you could have prevented. Universe rolling dice, and you happen to lose. But lightning isn't random, it's deterministic within its operating parameters, and that's actually better news than randomness would be, because deterministic means predictable. Predictable means manageable. Manageable means we can do something about it. We've learned to read the landscape the way lightning reads it. We see tall structures and know they are targets. We see isolated trees and understand the risk. We check storm forecasts and lightning detection maps and make informed decisions about when to be outside and when to seek shelter. We've built protection systems that save lives and property, lightning rods that channel strikes the safely to ground, surge protectors that shield electronics, building designs that turn dangerous strikes into manageable events, aircraft that fly through thunderstorms routinely because we understand how to let current flow harmlessly around the fuselage. We've gathered decades of data showing exactly where lightning goes and how often, photographed the same structures being struck repeatedly. We've documented Lake Maracaibo's nightly electrical display. We've tracked every strike in North America for years, building maps that show the patterns clearly. The evidence is overwhelming. The myth is dead, even if the saying survives. Maybe that's okay. Language changes slowly. Phrases outlive their original meanings. People will probably still say lightning never strikes twice for generations to come, using it as a metaphor for rare events, not thinking about actual lightning. But those of us who know the truth, who understand the physics, who followed this journey from myth to mathematics, we carry different knowledge now. We see storms differently, understand that the flash and crack and rumble aren't random chaos, but ordered phenomena, following rules as strict as gravity. There's beauty in that, not the beauty of mythology and divine intervention, but the beauty of a universe that makes sense, of patterns that can be discovered, of rules that can be learned and used to protect what we value. Lightning will strike tomorrow, 8 million times globally, just like today. Some of those strikes will hit empty fields and leave no trace. Some will start fires. Some will hit people who made unlucky choices about where to be, and many of them will hit the same towers, buildings and structures they hit yesterday and last week and last year, because physics doesn't forget, and doesn't need to. It just keeps solving the same equation, with the same variables, arriving at the same answers over and over. The storm has passed for tonight. The thunder is distant now, barely audible. The lightning flashes on the horizon, too far away to be dangerous. The air smells of ozone and wet earth. The danger has moved on to strike somewhere else, to find new targets or return to old ones. And you, lying there in the darkness, listening to the last rumbles fade, you know something your ancestors didn't. You know that lightning isn't a mystery, isn't divine judgment or cosmic randomness or anything supernatural. It's just physics, beautiful, powerful, relentless physics, following gradients and finding targets and returning to them whenever conditions align. The myth told us lightning never strikes the same place twice, but the truth is simpler and more profound. Lightning strikes where it must, returning to the same places for the same reasons, constant as the tides and as predictable as mathematics. The sky clears, the stars emerge between departing clouds, and somewhere on earth, right now, another bolt is falling. It knows exactly where to strike. It struck there before. It will strike there again. Not because it remembers, not because it chooses, but because the path of least resistance doesn't change just because you've used it before. The storm will return, maybe tomorrow, maybe next week, and when it does, lightning will find the same targets, the same towers reaching into the electrical fields, the same mountains piercing the clouds, the same isolated trees standing alone in fields. The myth is over. The truth remains. Lightning strikes twice, and 3 times, and 1,000 times, anywhere physics guides it, which is to say anywhere it struck before, and the conditions remain the same. That's the last thing to know, the final truth to carry forward. Lightning has no memory, but needs none. The landscape remembers for it. The towers and trees and mountains stand where they stood, tall and conductive and isolated, perfect targets yesterday, perfect targets today, perfect targets tomorrow. The thunder fades to silence, the night deepens, but the truth echoes on. Lightning knows where to go. It's always known, and now, at last, so do we. Sleep well. The storm has passed, but it will be back, and when it returns, you'll understand exactly what you're seeing. Not chaos, not mystery, not divine intervention, just lightning following its ancient rules, striking the same places it struck before, as it always will. The rumble fades, the story ends, but the lightning continues, forever returning, forever following the path of least resistance, forever proving that the old myth had it backwards from the start. Lightning strikes twice. That's the truth. That's what nature has been trying to tell us all along.